Pluto is a distant and dim, relatively small astronomical object that was once considered part of our solar system. However, recent and surprising announcements by leading space experts Neil deGrasse Tyson and Mayoku have brought Pluto back into the spotlight. They suggested that this remote body could potentially be on a likely crash course with Neptune. They aren't merely hypothesizing, they're issuing a warning. This miniature world may be heading straight for a catastrophic encounter with Neptune. But how could such a thing be possible? And what would the aftermath be if an enormous impact like that truly took place? Are we seeing an odd cosmic illusion, or is something far more tangible, and much more alarming, speeding toward us? Pluto's path comes dangerously close to Neptune's. Neil deGrasse Tyson and Mayoku are raising the alarm. If we've even made a small adjustment, we could be facing a devastating planetary accident. Might Earth be at risk as well? More crucially, how could such a cosmic occurrence even come to pass? Join us as we delve into the possible consequences of a Pluto-Neptune collision. Pluto, once officially a planet but later downgraded to a dwarf planet, remains a source of intrigue in the vast universe. As demonstrated by current models from leading researchers, Pluto's path passes perilously near Neptune's. Renowned astronomers Neil deGrasse Tyson and Michio Kaku are both alerting the world to a potentially dangerous interaction between these two bodies, which could imply a substantial hazard for Earth. Yet, how could this scenario unfold? Pluto's journey around the Sun is unlike any other orbiting body in our solar system. It takes an incredible 248 Earth years to complete one revolution. Since its discovery in 1930, it hasn't even made one full orbit. Still, the intrigue doesn't stop there. Pluto's orbital path is highly stretched out, much more so than the generally circular paths of the main planets. Even more fascinating is its orbital inclination, a tilt of 17 degrees compared to the Sun's plane. This trajectory is far more irregular than those of other planets, which adds layers of complication to Pluto's movement. Arguably one of the most fascinating aspects of Pluto's route is that it intersects Neptune's orbit. For about 20 years of Pluto's orbital cycle, it is actually closer to the Sun than Neptune, defying what we'd expect based on their standard positions. This raises the usual question: why haven't they collided? The answer lies in the gravitational effects of nearby celestial giants. Studies into Pluto's path began soon after it was discovered. Early astronomers attempted to make sense of its odd orbit. While most planets follow loops that align with the Sun's plane, Pluto's trajectory is slanted and uneven. The puzzle grew deeper when scientists realized Pluto's orbit overlaps that of Neptune. The stability of Pluto's motion, despite these strange features, proves the subtle intricacies of space mechanics. The three-body problem, understanding how three planets, similar to Pluto, Neptune, and the Sun, influence one another through gravity, is central here. It's like predicting future positions based on their initial placements and mutual gravitational pulls. In Pluto's case, this complexity reveals how its movement, Neptune's orbit, and the Sun's pull all work in an interlinked system. Terms like asynchronous oscillation, orbital drift, and VZK wobble are key to decoding this riddle, as highlighted by experts in astrophysics. What aids in maintaining celestial bodies on their stable routes is asynchronous oscillation. In Pluto's and Neptune's case, this means that when Pluto moves through Neptune's path, it is positioned at least 90 degrees away from Neptune, a safe angular buffer that prevents a crash. Orbital drift, on the other hand, involves the vertical displacement of a body as it circles. For Pluto, this suggests that when it draws near Neptune or another large planet, it is far above their orbital paths, adding another safeguard against potential impacts. Another important factor is the VZK wobble, named after researchers Zell, Kai, and Kaku, who studied the gravitational interactions of space objects. It describes how three massive entities, like Pluto, Neptune, and the Sun, exert forces on one another, influencing their movements. In Pluto's situation, the VZK wobble offers insight into why its orbit near the Sun appears erratic. Even though its path may seem unstable, this wobble helps keep it smoothly orbiting over very long periods. The VZK wobble shows that while space may seem chaotic, the unpredictability of the universe is governed by fundamental principles that still maintain a degree of stability. These forces support Pluto's consistent motion, preventing a Neptune collision or wild deviation. This three-body dynamic is vital to understanding how orbits shift due to gravitational interference. Studying it gives us more clarity about Pluto, our planetary group, and even distant galaxies. Computational models from the 1980s indicated that, while certain factors stabilize Pluto's orbit, it still exhibits unpredictability. Minor modifications in starting conditions can cause major deviations over centuries. Still, Pluto's orbit has remained steady over remarkably long durations. Modern automated data has allowed us to better observe how the massive planets, Neptune, Jupiter, and Saturn, influence Pluto's path across the solar system. Pluto and Neptune share a special orbital rhythm. For every 2 laps Pluto makes, Neptune completes 3. This synchronicity helps preserve Pluto's route. But Neptune isn't the only player. Jupiter's powerful gravity plays a major role in keeping Pluto's path stable. Saturn also contributes. Studies show that Jupiter's mass is sufficient to help maintain Pluto's trajectory for possibly billions of years. It appears that Neptune, Jupiter, and Saturn are collectively working to ensure Pluto travels safely through space, avoiding danger. These unusual but vital systems are crucial to keeping our solar system stable. Without them, space would be far more chaotic. Objects like Pluto might crash into others or be kicked out of the system, creating chain reactions across the cosmos. Particularly in Pluto's case and concerns about future encounters with Neptune, understanding its movement is crucial. This provides us a clearer view of the ever-changing, dynamic nature of our planetary family. Pluto's case shows how even seemingly unstable orbits can achieve harmony through complex gravitational and kinetic balances. It also highlights the need for constant observation and analysis of these anomalies to better understand our place in the universe. Exploring space's farthest reaches often brings us face to face with the strange nature of celestial phenomena. Pluto's orbit is a perfect representation of such irregularity. The concept of orbital chaos, which refers to how orbits are highly sensitive to their starting conditions, is clearly at play here. For Pluto, this means that even tiny changes in its speed or position can dramatically alter its long-term path. Using computer simulations has greatly aided scientists in examining Pluto's behavior. These tools use complex models to forecast its trajectory. Accounting for gravitational pulls from nearby planets, solar radiation, and even hypothetical external factors like passing stars or dark matter fluctuations. Thanks to these simulations, astronomers can observe how Pluto's path might change over millions, or even billions, of years. Despite its small size, Pluto commands significant attention due to the unpredictability of its orbit. This unpredictability, while subtle in the short term, can lead to drastically different outcomes over long timescales. The possibility of a future collision with Neptune, while remote, isn't entirely outside the realm of cosmic dynamics. To date, no models have shown an immediate risk of impact. However, what Tyson, Mayoku, and other experts warn about isn't necessarily a collision tomorrow, it's the need to continuously observe and refine our models, because even minuscule forces, over enough time, can lead to profound consequences. The Pluto and Neptune situation is also a valuable case study in planetary motion and long-term orbital mechanics. It illustrates the importance of celestial resonance, the rhythmic gravitational relationships between orbiting bodies. Without the precise 3:2 resonance between Pluto and Neptune, their paths might have crossed dangerously long ago. Resonance isn't just a lucky coincidence, it's a stabilizing force in celestial mechanics. Many moons and planets across the solar system participate in such harmonies. For Pluto and Neptune, their resonance ensures that even when Pluto appears to cut through Neptune's orbit, they are never in the same place at the same time. Their dance, though seemingly chaotic, is choreographed by gravity in ways we're only beginning to fully comprehend. But as our solar system moves through the Milky Way, external factors come into play. Interstellar objects, rogue planets, or gravitational waves from nearby supernovae could someday influence the delicate balance we've come to depend on. The real takeaway from the Pluto-Neptune interaction is not fear, but awe. It reminds us that the universe operates on principles both subtle and powerful. Forces we cannot see with the naked eye keep entire worlds in motion, preventing chaos on unimaginable scales. It also reminds us of our duty to keep watching, learning, and modeling. The tools we use today, advanced telescopes, machine learning algorithms, and orbital simulation engines, are our modern lighthouses. They help us navigate the vast, dark ocean of space and prepare for whatever cosmic tides may come our way. In the grand narrative of the cosmos, Pluto might seem like a minor character, but its story offers profound insights into the invisible forces that shape our universe. Formulas to replicate how Pluto and planets like Neptune interact through gravity show that by tweaking initial variables, researchers can observe how even minor adjustments may completely change Pluto's destination. Back in the 1980s, digital models unveiled a startling feature of Pluto's orbit. Despite built-in stabilizing factors like asynchronous oscillation and orbital drift, Pluto's journey can still act unpredictably. A slight difference in its starting location or velocity could produce vastly different outcomes in just a few years. Nevertheless, Pluto's path has held steady over billions of years. This indicates that, underneath its erratic appearance, lies a hidden consistency. Predicting the motion of celestial objects, especially those with erratic orbits like Pluto's, remains an enormous challenge. The inherent instability of such systems makes long-term predictions full of uncertainty. While mathematical models are excellent tools for understanding and predicting space dynamics, they also show our limitations. These calculations rely heavily on accurate starting values, and even a small error can lead to drastically different results, making precision very difficult. Beyond the unpredictable nature of orbital paths, Pluto also represents the continual transformation and movement within the cosmos. Despite humanity's considerable achievements in astronomy, Pluto's unusual behavior reminds us how much we've yet to learn. Studying how massive planets shape Pluto's movement helps us understand solar system dynamics better. It shows that each planet's mass and location can significantly influence others. So why are high-profile astrophysicists suddenly worried about a potential Pluto-Neptune impact, despite all the cosmic mechanisms designed to avoid it? Neil deGrasse Tyson, a celebrated scientist and leading voice in public astronomy, offers a unique take on our planetary puzzles, especially Pluto's unusual story. Tyson, known for advocating Pluto's reclassification as a dwarf planet, provides insightful commentary on how our understanding of orbits and the solar system evolves over time. He fails to notice the shift in Pluto's status as disrespectful, but rather as a necessary correction based on growing scientific knowledge. Tyson believes that learning and adaptation are central to grasping complex orbits. He views trajectories like Pluto's as a sign of how much more there is to discover. The wonder behind such mysteries keeps astronomy exciting. Yet, while Tyson is generally optimistic, his view of a potential Pluto-Neptune collision is far more sobering. His concern about Pluto's fate, once an official planet, stems from his awareness of orbital instability. He acknowledges that Pluto has stayed safe so far, but even tiny changes accumulating over time could lead to disaster. Pluto's orbit, especially its overlapping section with Neptune, forms a fragile cosmic rhythm that may not last forever. Tyson argues that even minor shifts in Pluto's movement could lead to major consequences over thousands or millions of years. Such disturbances could cause chaos or even a direct collision. Though this is not an immediate threat, it's a possibility unfolding on a time scale far beyond human civilization. Still, Tyson's cautious tone stresses the importance of continued vigilance and further study of Pluto's orbit. Tyson isn't alone. Michio Kaku, a world-renowned theoretical physicist, also sees the possible mayhem that might result from planetary interactions. Like Tyson, Kaku is amazed by the universe's vastness, but he also comprehends the fragile equilibrium of planetary systems and the unpredictable outcomes that may arise. Both Kaku and Tyson emphasize the importance of relentless exploration into the invisible forces guiding orbital paths and the long-term future of our solar family. In conclusion, Pluto's circumstances reflect how our knowledge of the universe is in constant motion. Each discovery opens new questions. As astronomy advances, the slight chance of a Pluto-Neptune impact serves as a humbling reminder. The universe is full of surprises, and even seemingly peaceful planetary paths can shift drastically over time. Pluto's lessons motivate us to continue looking up, and to keep wondering what secrets the stars have yet to reveal. This fascination with Pluto is not only about orbital mechanics, it also speaks to a deeper human impulse, our need to understand the unknown. For centuries, the night sky has inspired curiosity, myth, and scientific inquiry. Pluto, distant and dim, symbolizes both the limits of our reach and the boundless potential of our intellect. Modern space agencies and observatories continue to refine their instruments, hoping to gather more data on Pluto's exact position, composition, and orbital behavior. The New Horizons mission, which flew by Pluto in 2015, revolutionized our view of the dwarf planet, revealing ice mountains, a heart-shaped glacier, and signs of geological activity. These discoveries painted a picture of a world far more complex than previously imagined, one that defies its small size and remote location. But even with high-resolution imagery and spectral analysis, questions remain. How stable is Pluto's orbit really? Are there unseen forces at play, perhaps minor moons, Kuiper belt objects, or distant gravitational influences, that affect its path in ways we don't yet understand? And what does Pluto's long-term motion reveal about the early dynamics of the solar system itself? Astrophysicists increasingly view Pluto not as an anomaly, but as a critical piece of the puzzle. Its eccentric orbit, highly inclined and intersecting with Neptune's, is believed to be the result of ancient gravitational encounters, possibly even with rogue planets that no longer exist. As such, Pluto serves as a time capsule of sorts, preserving the memory of a wilder, more chaotic solar system. Understanding such a celestial body doesn't just satisfy intellectual curiosity. It has practical implications. A clearer grasp of orbital mechanics and gravitational resonance patterns could improve everything from satellite deployment to the long-term sustainability of human outposts beyond Earth. It could even inform the way we one day navigate the asteroid belt, mine Kuiper belt objects, or avoid cosmic hazards. Ultimately, Pluto reminds us that even in a universe governed by laws and equations, mystery endures. And within that mystery lies the promise of discovery, the driving force of astronomy.